Okay, so now welcome back. So in this video we will talk about the cotangent function. I suppose in the previous video we talked about the tangent function. Let me take a look here. Okay, cos and tan, right. So the cotangent function is again the same story, almost the same story as the tangent function, which means that if basically the cotangent function, the definition is basically, so we have the cotangent function and definition is cot as a function from R minus basically all the multiples of pi, meaning that all the basically you can imagine that 1 pi, 2 pi, 3 pi, 4 pi, and negative 1 pi, negative 2 pi, and so on and so forth, even 0 pi, subtracted from the domain of the function, meaning that you can write R minus basically x such that x is equal to n times pi and belonging to the set of integers, and the codomain of the function is R, right? So n times pi means basically n belonging to the set of integers, meaning that 0 times pi, 1 times pi, 2 times pi, 3 times pi, and so on and so forth, all the way up to n times pi. And then you have also in the other direction you have negative times pi, negative 2 times pi, negative 3 times pi, all the way up to negative n times pi. Of course, n here belongs to the set of integers, meaning that you are multiplying all integers by pi, and all of those multiples will be subtracted from the domain of the function, which means that and the reason for that is that basically the cot function, when you say cot of x, that's the same thing as that's as we argued before. We said that cot is the reciprocal of the tan function, so 1 over tan of x, and that means that basically and tan of x is the same thing as sine of x over cos of x, and so the reciprocal of this would be cos of x by sine of x. Would be cos x by sine x. That means that wherever sine of x is equal to 0, then of course cot x is not defined. Now sine of x is not defined, is equal to 0 at all the multiples of pi, of course, because as you know, if you have a unit circle here, then 0 times pi is equal to 0, right? So 0 times pi would be equal to 0, which would be, for example, 0 degrees or 0 radians, depending on well, let's take it as 0 radians. And so 0 would be this angle here, and here you know that basically sine 0 is equal to 0. Then when you get to pi, again sine pi is equal to 0. So that would be 1 times pi is equal to pi. Then if you multiply pi by 2, you will get 2 times pi is equal to 2 pi, which gets you here. From here basically gets you here. And 2 pi, basically the sine of 2 pi, of course, again is equal to 0. Then if you multiply this by 3 pi, it will get you here, and 3 pi would be, again, the sine over here would be 0. And the reason why the sine at this angle and at this angle are 0 is because we said that basically we always calculate we measure the length of the sine of an angle across along this vertical axis, either here or here. If you move from here all the way up to here, that would be a 1. If you move from here all the way up to here, that would be a negative 1. Which means that, for example, if you have some angle like, for example, 30 degrees, let's say you have the angle, for example, 30 degrees. So 30 degrees, the sine of that angle would be simply this length along the y-axis, which is, for example, I know that, for example, sine of 30 degrees is equal to 1/2, if I'm not mistaken. I have forgotten most of these things. If you go to degrees and if you write sine of 30 degrees, that's equal to 1/2. And what that means is that 1/2 is actually 1/2 of this distance from here all the way up to here. And when you draw a 30-degree angle, it comes all the way up to halfway between these 2 points, and then you measure it. You measure that length along the y-axis up here, and that's equal to 1/2 actually, meaning that half of a unit. So then what that means is that again, you measure this you measure the measure of the sine of an angle along the vertical axis, and if your angle is some angle in the first quadrant, it's going to be positive. In the second quadrant, it's going to be positive, meaning that if you have some angle over here, the sine is going to be up here and it's positive value. If it's some angle in the second quadrant, it's still going to be a positive value. If your angle is some angle in the third quadrant, as you can see, it's a negative value. In the fourth quadrant, as you can see, the angle is going to be a negative, the sine of the angle is going to be a negative value. But specifically at these 2 points, at basically theta is equal to 0 and 2 pi and pi, and all the multiples of these angles, all the multiples of 0, all the multiples of pi, and all the multiples of 2 pi, of course the sine of, meaning all the angles coterminal with 0, 2 pi and pi, of course the sine of the angle is going to be equal to 0 because there is no elevation, there is no height here to measure. The height is actually 0. And as soon as you start increasing your angle, for example, suppose you're at 0, of course the height is 0, meaning that 0 would be some angle like this. And then suppose that you make your angle 3 degrees. So let's say that this is 3 degrees. And if you make it 3 degrees, then you will have some elevation along the y-axis, and you can measure this length, and that would be the sine of 3 degrees basically. Otherwise, if you're 0 degrees, your sine of course is 0 because the height is 0. If you're at 2 pi, it's again the same angle, the sine is 0. And if you go all the way up to here, which gives you basically 2 pi, again over there is no elevation with respect to the y-axis or the vertical axis. So again, your sine is going to be positive, is going to be 0 over there. And so that's basically the whole story. Meaning that whenever basically the sine function gives you a 0 output, then that 0 goes to the denominator here and makes cot of x undefined. And for the same reason, they have taken all of those multiples of pi out. 0, negative 1, 1, 2, all the way up to infinity and negative infinity. So long story short, basically what they have done is that the domain of the function, they have defined it as R minus the set of all x's such that x is equal to n pi, n belonging to the set of integers, and the codomain of the function is R. That is basically the whole, everything about the cot function. Now let's draw the graph of the cot function as well, so that we know what that looks like. So the cot function is basically a function that of course you know that the function is not defined at multiples of pi, meaning that if I draw a unit circle over here, and if I draw a circle here, and let me see. Okay. And then okay. Now, I didn't actually want to have this color. I don't know where it came from, but it's actually okay. I mean, there is no problem with that. Now, if I create a table of values for the cot function, so first of all, and the definition for the cot function is that basically cot of x is equal to cos of x by sine of x. Now, let's see what happens at 0. At 0, basically at 0 degrees, basically the sine of x is 0. So then the cot of x, so if I call this theta, for example, and call this cot of theta, since sine of x is 0, then cot of x is undefined. That is at 0 degrees. Then at pi by 2, so this is 0, this is, let's say 90, since I'm doing everything in degrees. So this is 90 degrees, this is 180 degrees, this is 270 degrees, and this is 360 degrees. So when I get to 90 degrees, what happens is that cos of 90 degrees is equal to 0, and sine of 90 degrees is equal to 1. So 0 divided by 1 is equal to 0. So you get to 0 at 90 degrees. At 180 degrees, the cos of theta becomes -1, the sine of theta becomes 0. So then there you are undefined. So these are all the multiples of pi where the function is not defined. Then when you get to 270 degrees, at 270 degrees the cos of x is 0. And so since the cos of x is 0, the whole thing becomes 0. And when you get to 360 degrees, again, since it's a multiple of pi, then of course you are undefined, because over here at 360 degrees the sine is 0, so cot would be undefined. Now let's go in the other direction as well a little bit, for example all the way up to -2 pi, or all the way up to -360 degrees. Going in this direction, this angle becomes -90 degrees, or negative pi by 2. So -90 degrees would be this angle here. So over here your cos is 0. So of course the whole thing becomes 0, because cos 0 divided by anything is 0. And then you have at -180 degrees, your cos is going to be equal to -1, your sine is 0. So here the function is undefined. When you get to -270 degrees, over here your cos is 0, and so the whole function goes to 0. The whole cot function goes to 0. And at -360 degrees, which is right here, the sine is 0, so the function is undefined. Now again, wherever your function is undefined, which is basically this point, this point, this point, this point, and this point, at these points, basically you will get all those vertical asymptotes, which means that, let's say that this is 0, 0, there you have 0 and 90 degrees, and 180 degrees, and 270, and 360, 1, 2, 3, 4, so 1, 2, 3, 4 here. So at 0 the function is undefined. That means that you will get a vertical asymptote right on the y-axis. At 180 degrees, the function again is undefined. So this is 180 degrees. You will get a vertical asymptote here. At 360 degrees, again, you will get a vertical asymptote here. At -180 degrees, you will get a vertical asymptote here. And at -360 degrees, you will get a vertical asymptote here. And this is your y-axis, this is your x-axis. And at x is equal to 90 degrees, your output is 0. At x is equal to 180, 270, your output is 0. And at this output, you are undefined. At negative 90 degrees, the output goes to 0. At -270 degrees, the output goes to 0. And then again, you will get some function like this, meaning that you will have some function like, it's just like the tan function, except that the orientation of the function is different, meaning that in the case of the tan function, the difference between the tan function and the cot function is that, of course, the tan function is defined is undefined basically at odd multiples of pi by 2. So the tan function is undefined at odd multiples of pi by 2. But the cot function is undefined at, well, all the multiples of pi, of course, considering the fact that meaning at n times pi, of course, n belonging to the set of integers. And over here, you're undefined at 2n plus 1 times pi by 2, right? But again, n here belongs to the set of integers, which means that you're undefined over here. You're undefined at odd multiples of pi by 2. Odd multiples of pi by 2 are basically, for example, you can go in the positive direction, you'll get pi by 2. You will get 3 pi by 2. You will get basically 5 pi by 2, and so on and so forth. In the negative direction, you are undefined at negative pi by 2, negative 3 pi by 2, negative 5 pi by 2, negative 5 pi by 2, and so on and so forth. Which means that the tan function is going to give you basically, this is pi by 2, this is pi, this is 3 pi by 2, this is 2 pi. And if you do the same thing over here, the function is going to be undefined at pi by 2, for which you will get a vertical asymptote. Then you have pi, and then you have 3 pi by 2, at which point you are undefined. And then again at negative pi by 2, the function is undefined. And then again at that's negative pi, negative 3 pi by 2 over here, the function is undefined. And we saw that basically the value of the function at these points were 0, which gives you a function like this. This is the tan function. And then this behavior is repeated all throughout the domain of the function, right? This is f of x is equal to tan x. Now f of x is equal to cot x. These horizontal asymptotes, these vertical asymptotes occur at different points throughout the domain of the function, meaning that they occur at the multiples of pi, not at the odd multiples of pi by 2. Meaning that you can imagine that you have pi by 2 over here. You have pi, you have 3 pi by 2 and 2 pi, and then you have again negative pi by 2, negative pi, negative 3 pi by 2, negative 2 pi. And then you have to go, first of all, at 0, the function is not defined because it's a multiple of pi. So you get one of those asymptotes right on the vertical axis. And then at pi, again, the function is not defined, so you get one of those asymptotes there. At 2 pi, you're not defined, you'll get one of those asymptotes there. At negative pi, the function is not defined. At negative 2 pi, the function is not defined, so you'll get those asymptotes there. Moreover, you will have basically the output of the function is 0 at these points, as we saw over here, right? So the function is 0 at these points. Now what happens is that you see that the tan function is basically going, meaning that if I call each of these basically this is basically one complete period of the function, right? Meaning that it goes from negative infinity all the way up to positive infinity, and again starts from negative infinity all the way up to positive, or you can say that it's a periodic behavior of the function. So throughout, if you consider any of these periodic behaviors of the function, you can see that I can call this the right leg of the function, and I can call this the left leg of the function. Of course, these are my own words. These words are no standard words in mathematics, of course. So this right leg is, the values for this right leg are all positive. The values for this left leg are all negative, meaning that it gives you this kind of orientation, this kind of direction to the function. But in the case of the chord function, the orientation is going to be the reverse of this orientation, meaning that you would get some graph like this. I will show you the graph right here. So the graph in the case of the chord function is going to be something like this. It is going to be something like this, right? The complete opposite of this behavior. You see? And you need to take note of this behavior of the function and see what it's doing, and then you will be able to use this function, meaning that, for example, this kind of function, as you can see, is going from you can see that this function, you can see that this is y is equal to, or f of x is equal to cot x, right? Now you can see that this function, every pi by 2 units, first of all, you can see that the function is not defined at multiples of pi. So that's one thing that you need to know about the function, so that if you want to use it, for example, you want to use it in physics, you're doing some sort of experiment or something, you have some data, and you want to model your data after the cot function, for example, for some particular purpose. So of course you need to know where the function doesn't work. So for example, you know that this function, since it's not defined as multiples of pi, it doesn't work at those values, meaning that for those values you cannot rely on this function. This function doesn't work at the odd multiples of pi by 2. So if you're doing something and you need to have outputs at those values at those multiples of pi by 2, then this function would not work, unless of course you could make changes to this as well, meaning that there is ways that you could actually shift the whole domain of the function to the right or to the left by whatever, but by how many ever units you want. For example, you can shift the domain of this function, for example, pi by 2 units to the right, and then all of these, the whole function will be transferred pi by 2 units to the right, meaning that, for example, now you can see that this vertical asymptote is occurring at x is equal to 0, then it would be occurring at x is equal to pi by 2, then this would be occurring at, for example, this point, this would be occurring at pi by 2 units after that, and so on and so forth. Of course, you can do that sort of thing. But, if you want to use the standard function, you know that the standard functions, as far as the function in standard configuration behaves, the function is not defined as at multiples of pi. This function is not defined at odd multiples of pi by 2. And you can see that this function, you can see the shape of this function goes from the very beginning of the cycle. The function starts at positive infinity and starts basically decreasing and goes all the way up to negative infinity. This function, what it does at the beginning of the cycle, it starts from negative infinity and starts increasing all the way up to positive infinity. So this is how you know where you can use these two types of functions. Okay, so that's basically the cut function. Now let's figure out why basically the function behaves this way, and then we will get to the next function. Okay, so now let's see why the cut function behaves the way that it does, meaning that from the beginning of the cycle it starts from positive infinity and decreases gradually and goes all the way up to negative infinity, and it does the same thing over and over again, every pi units basically. And the tan function does the exact opposite of that every pi units, right? Now, so you know that the output of the function at x is equal to 0 or at theta is equal to 0 is, of course, is undefined, meaning that you'll get a vertical asymptote over here. Now when basically when you start from very close to this asymptote, meaning very close to theta is equal to 0 degrees, for example, basically the function that we are dealing with is basically f of x is equal to cot x, which is the same thing as basically cos x, which is the same thing as cos x over sine x. So you have cos x over sine x. So when x is very, very close to 0 degrees, so let's say that, for example, 1 degree or so, cos of x is very close to 1. Cos of x is very close to 1 when x is approximately, x is very, very, very close to, I don't know how to write that mathematically. When x is very close to 0 degrees, then basically sine of x is, cos of x is very close to 1. Very close to 1. And sine of x is very close to 0. So what that means is that you have a you're dividing some value very close to 1, for example 0.9999, and basically you are dividing that by some value which is very close to 0, meaning that you're dividing that by 0.000001, for example, something like that. And so you will get some value like 1, 2, 3, 4, 5, 6. So if I multiply both the numerator and denominator by a factor of, for example, 1 million, I will get something like, for example, 1 million times this number would be something like 9999 and 2 zeros in front of it, so that would be 99999, actually 999900, and then divide by 1, which is something like 999,900 or so. And so you can see that very close to 0, that the output of the function is considerably large, meaning that you will end up somewhere over here. And now what happens is that when x, let's go halfway through, and let's see what happens at, for example, or let's get to, for example, 45 degrees. So at 45 degrees, when x is equal to 45 degrees, then cos of 45 degrees, as you know, is equal to square root of 2 over 2. Sine of 45 degrees is equal to square root of 2 over 2, which means that at 45 degrees, your output is going to be basically exactly cos of 45 degrees by sine of 45 degrees, which is exactly equal to 1, which means that your output is exactly at 1. Let's see what happens at x is equal to, for example, 90 degrees. At x is equal to 90, cos of 90 degrees is equal to 0, and sine of 90 degrees is equal to 1. And that means that the output of the function is at 0, right? So you can see how the function is actually behaving. When I get to, for example, 135 degrees, that is the same thing as 135 degrees. That is the same thing as 90 plus 45, right? So 90 plus 45, if you want to calculate it would be interesting actually to see this in the unit circle. So suppose that you have, let me show you this, let's calculate the sine of 135 degrees and the cos of 135 degrees on a unit circle and see what happens. And I will also show you the same thing using the formulas that we have in trigonometry. And of course, those formulas are again based on the unit circle. They make your work considerably easy compared to working with the unit circle itself. But if you happen to forget those formulas, the unit circle is always at your disposal. So suppose that you have the unit circle here, and select some border here and edit, fill with foreground color, for example, and that is my unit circle, right? Now this is 45 degrees. This is 45 degrees, this is 90 degrees, and this is 135 degrees. So at 135 degrees, you can see that the sine, we said that the sine we measured along the vertical axis, which means that the sine would be this value over here, meaning that this value, this exact value is the sine of 135 degrees. The cos of this angle, I have to measure it along the horizontal axis, meaning that this would be, meaning that this distance here is basically the sine, the cos of 135 degrees, right? Now you can see that if I draw an angle of 45 degrees in the first quadrant, you see this is an angle of 45 degrees and it is in the first quadrant. Basically the sine of this angle is exactly the same as the sine of this angle, which is 135 degrees, meaning that you can say that the sine of 45 degrees is actually exactly equal to the sine of 135 degrees. And you can write the sine of basically 135 as 90 plus 45 degrees. That is basically one interesting thing that you can see in the unit circle. One more thing that you can see here is that the cos of 135 degrees, which is this value over here, it's exactly the same as negative of the sine of 45 degrees, because the sine of 45 degrees is basically this value here, and if you measure these two distances are exactly the same. This is the cos of 45 degrees, meaning that you can say that the cos of 135 degrees is exactly equal to negative of the sine of the cos of 45 degrees. And so what that means is that now if I have the cos of 45 degrees, which is square root of 2 by 2, so that means that the cos of 135 degrees is negative square root of 2 by 2. The cos of 135 degrees is equal to negative square root of 2 by 2. And since the sine of 45 degrees is exactly equal to the sine of 135 degrees, the sine of 45 degrees is equal to square root of 2 by 2. And therefore I can conclude that the sine of 135 degrees is equal to the sine of 45 degrees, which is equal to square root of 2 by 2. That's how you can calculate these two values. Moreover, what you can do is that you can use the formulas that we developed in I haven't actually recorded those courses yet, but let's assume that I have already done that, because I have already done that in some courses, and for some reasons I cannot publish them yet. I have to redo the courses. But we said that in those courses we drew a unit circle, and based on the unit circle we concluded actually the following, meaning that what we concluded was that if I'm not mistaken, I hope that I can remember the formula. Okay, so now another way of doing the same thing, meaning that another way of showing that basically the cos of 135 degrees is equal to negative cos of 45 degrees, and sine of basically 45 degrees is equal to sine of 135 degrees. So another way of doing that is using the formulas that we have developed in trigonometry, right? And those formulas are I'm going to tell you about these formulas very briefly, but you should be able to use them throughout this course at least, which is basically as follows. There is only a couple of formulas that you will need in order to be able to use the whole, basically the whole unit circle in terms of formulas. So the first thing that you need here is that, now I don't know whether I told you about, well, the first thing that we need here is basically you need a couple of formulas like sine of negative x, which is equal to negative sine x. And why that is that basically if you have a unit circle here, and if you have this, basically if you have some angle x over here, let's say that this is some angle x. If this is x, then basically negative x would be this angle over here, right? So if this is x, this is negative x, and you can see that sine of negative x is basically this thing over here, this distance over here, call it a, for example. Sine of negative x would be this distance over here, which is equal to b, and you can see that a is equal to negative b, or you can say that b is equal to negative a, right? So this is exactly the same, meaning that the absolute value of a is equal to the absolute value of b, but of course b is a negative value, a is a positive value, which means that b is equal to negative a, right? And so you can say that then a is the same thing as sine of x. A is the same, or you can say that the sine of negative x is equal to b, and basically sine of x is equal to a, so that's negative a. Or you can say that sine of negative x is equal to negative sine x, right? So that is about the sine of negative x is equal to negative sine x. Next, what we have is basically the cos of negative x is equal to cos x. And the reason for that is that if you have a unit circle here, and if you put the unit circle here, right here, and then suppose that you have some angle over here, for example, if I take this as x, if I take this angle as negative x, then the cos of this angle x is going to be this distance on the horizontal axis. The cos of this angle, of course, if my circle was perfect, then these two would be exactly the same distances, which means that cos of x is actually equal to the cos of negative x, because as you can see, well, they are actually the same value. So cos of negative x is equal to cos x. And then what the next thing that you need is basically other trigonometric ratios. For example, sine, cos, tan of negative x is the same thing as sine of negative x over the cos of negative x, which is equal to sine of negative x is equal to negative sine x, cos of negative x is equal to cos x, and that is equal to negative tan x. So tan of negative x is equal to negative tan x. And then you have the cot of negative x. The cot of negative x is equal to cos of negative x over the sine of negative x, which is equal to cos of x over negative sine x, which is equal to negative cot x. which means that cot of negative x is equal to negative cot x. Now we have secant x, secant of negative x is equal to basically 1 over cos of negative x, right? So, and that is equal to 1 over cos x, which is equal to secant x. So secant of, that means that secant of negative x is equal to secant x. And also cosecant of negative x is equal to 1 over sine of negative x, which is equal to 1 over sine of negative sine of x, which is equal to negative cosecant x. Which means that cosecant of negative x is equal to negative cosecant x is equal to negative cosecant x, right? So long story short, I can write sine of negative x is equal to negative sine x, cos of negative x is equal to cos x, tan of negative x is equal to negative tan x, cot of negative x is equal to negative cot x, cosecant of negative x is equal to actually secant x, and cosecant of negative x is equal to negative cosecant of x, which means that the only, you can see that cos of negative x is equal to cos x, and secant of negative x is equal to secant x, and the reason that these two are the same and the other four are behaving similarly is that basically cos of x is equal to 1 over secant x, or you can say that basically secant x is equal to 1 over cos x. These are reciprocals, and so they behave the same. Now, the next thing that you need to know about these formulas is that there are 4 formulas that you need to understand, and then based on those formulas you can derive essentially everything that you need in trigonometry, meaning that you have basically so the first formula that we have is cos of x plus y. So we know that cos of x plus y is equal to cos x cos y minus sin x sin y, right? And we know this based on geometric proof, based on geometric or construction proof. So we know that cos of x plus y is equal to cos x cos y minus sin x sin y. We have proved this geometrically, but it would take a long time to prove this, so I'm not providing the proof here. We hopefully, if you have taken the previous course on trigonometry, you have already seen this. Now, if I instead of basically in order to calculate cos of x minus y, what I can do is that in this formula I can substitute y with negative y, meaning that I can write the same formula as basically cos of x plus negative y, and the cos of x plus negative y is equal to, based on this formula, that gives me cos of x, cos of negative y, minus sine of x, sine of negative y, right? Now we know that cos of x, well, it remains cos of x, cos of negative y is equal to cos of y, and sine of x is sine of x, and sine of negative y is negative sine y, which means that that is cos x cos y, negative into negative is positive, plus sine x sine y. So I can write cos of x minus y, I can write it as cos x cos y plus sine x sine y. Now there is a couple more things here that we need to discuss, and that is basically cos of, for example, pi by 2 minus x. We are going to need these in order to prove the next results. So cos of pi by 2 minus x, if I want to calculate this, I can calculate it based on this, which gives me basically cos x cos y, which is cos pi by 2 cos x, plus sine x sine y, which is sine pi by 2 sine x, right? Now cos pi by 2 is equal to 0, so the whole thing, this goes to 0. Sine pi by 2 is equal to 1, so this becomes sine of x. And there is another result that we are going to need as well, and that is sine of pi by 2 minus x. So this was cos of pi by 2 minus x. Now sine of pi by 2 minus x is equal to I can use this formula. You can see that sine of x is equal to cos of pi by 2 minus x, right? Which means that I can take this whole thing as x here, right? And then write this as cos of basically pi by 2 minus, and this whole thing becomes x here. So minus basically pi by 2 minus x, right? So what I've done is that I know that sine of x is equal to this cos of pi by 2 minus x. So that means that sine of any angle, if I take that angle as x, is going to be equal to cos of pi by 2 minus x. So now I have written this as cos of pi by 2 minus x, right? So that gives me basically cos of pi by 2 minus pi by 2 plus x, which is equal to, and basically these two will cancel out, and then you have cos of x. That means that sine of pi by 2 minus x is actually equal to cos x. Right? So that is that. Now if you want to find, now there is two more formulas that we need to develop here, which is basically sine of x plus y and sine of x minus y. Sine of x plus y and sine of x minus y, which is equal to, for sine of x plus y, what I can do is that I know that sine of x is equal to cos of pi by 2 minus x. So I can write this as cos of pi by 2 minus x, which is x plus y. And now that is basically the same thing as cos x minus cos y, right? Which is, of course, at this point in time, we don't have actually that formula. But what I can do is that I can write this as cos of basically pi by 2 minus x and minus y basically, right? I can write this as cos of pi by 2 minus x minus y. Just multiply this negative by this x and y, and then put these two together and take the cos of that. So we said that cos of pi by 2 minus x is equal to so we said that cos of x minus y is equal to cos x cos y. So this is equal to cos x cos y, or actually cos, I have to write the formula as it is. So cos x would be here pi by 2 minus x, and cos y would be cos y basically. So we have cos of x minus y, cos x cos y, plus sin x sin y. So sin x would be sin pi by 2 minus x, and times sin y, right? So which means that basically cos of pi by 2 minus x, over here we said that it's equal to sin x, that is equal to sin x, cos of y is equal to cos of y, sin of pi by 2 minus x is equal to cos x, is equal to cos x, and there you have sin y, which means that sin of x plus y is equal to sin x sin y plus cos x cos y, right? Which means that sin of x plus y is equal to sin x cos y plus cos x sin y. And we can now calculate, based on the same formula, we can calculate sin of x minus y, which I can write simply, I can write this formula as sin of x plus negative y, and then I will have sin x cos negative y plus cos x sin negative y, which is equal to sin x cos of negative y is equal to cos y, and cos x sin of negative y is equal to negative sin y, which means that I have sin x cos y minus cos x sin y. So that means that sin of x minus y is the same thing as sin x cos y minus cos x sin y, right? So now we have all of these formulas, and they are very useful, meaning that, for example, when you want to calculate the cos of 135 degrees, what you can do is that basically I want to calculate the cos of 135 degrees. So what I can do is that I can write it as, for example, 90 minus or 90 plus 45 degrees, right? So I can write this as the cos of 90 plus 45 degrees. And then cos of x plus y is equal to cos x cos y, so cos 90 degrees, cos basically 45 degrees, and minus sin x sin y, so minus sin 90 degrees, cos, sin of 45 degrees. Now cos of 90 degrees is equal to 0, so this whole thing becomes 0. Sin of 90 degrees is equal to 1, so that's equal to sin of 45 degrees, and you have a negative sign here as well. Sin of 45 degrees is square root of 2 by 2, which becomes negative square root of 2 by 2, which is which is of course equal to you know that the cos of 45 degrees is actually equal to square root of 2 by 2. So you can write this as negative, basically cos of 45 degrees, which is equal to negative square root of 2 by 2. So that's how you can find, for example, the cos of 135 degrees. Or what you can do using these formulas is that, for example, you want to calculate the sine of 135 degrees. So what you can do is that you can write this as sine of basically 90 plus 45 degrees. And then you have basically sine x plus y. We said that it's equal to sine x cos y is equal to sine x cos y. So sine 90 degrees plus sine x cos 45 degrees plus cos x sine y plus cos 90 degrees sine 45 degrees. Now sine 90 degrees is equal to 1 and cos 45 is square root of 2 by 2. So this is equal to 1, this is square root of 2 by 2. Cos 90 is equal to 0. So this whole thing becomes 0. And therefore, this is equal to square root of 2 by 2, which is actually equal to, and you know that basically the sine of basically 45 degrees is actually equal to square root of 2 by 2. So this is equal to, this is equal to the sine of 45 degrees as well, right? And this was negative cos of negative cos of 45 degrees, right? Now you can see the same thing on the unit circle as well, meaning that if you have a unit circle here, so you have basically 135 degrees is this angle over here. This is 135 degrees. And 45 degrees is this angle over here. Let me actually do a good unit circle because I want to show you exactly what I mean by this. So I'm going to draw a unit circle here and then select the border. Okay. Okay, so then what I can do is that I know that basically cos of 135 degrees is this angle here. This is 135 degrees. Now the cos of 135 degrees is basically this value here. This value here is basically, this value here is the cos of 135 degrees. And using the formula, we said that it's equal to negative cos of 45 degrees. So cos of 45 degrees, if this is 45 degrees, the cos of 45 degrees would be this value over here. This is cos of 45 degrees. So as you can see, these are exactly the same lengths on the horizontal axis. So you can see that, well, cos of 135 degrees is a negative value. Cos of 45 degrees is a positive value, but the length of the two distances are exactly the same, meaning that you can say that, based on this, you can say that the cos of 135 degrees is equal to negative cos of 45 degrees, right? But the sine is actually the exact same value, meaning that 45 degrees, 135 degrees, the sine of them is exactly this distance on the unit circle. Exactly this vertical distance. Which means that you can say that basically the sine of, you can say that the sine of 45 degrees, you can say that the sine of 45 degrees is exactly equal to the sine of 135 degrees, right? And of course, there is a ton of things that you can do with these formulas, meaning that using this formula and this formula, and of course these two are not that important. These basically you can derive based on these formulas, but using these four formulas, 1, 2, 3, and 4, you can derive all kinds of formulas for example, what is cos of pi by 2 minus x, cos of pi by 2 plus x, what is cos of pi minus x, cos of pi plus x, and so on and so forth. And that you can use in all kinds of different situations. But yeah, and that is basically what you can do with this. Now, what we were discussing here, and we got into this discussion, was that we got into basically we got into this business of, I don't actually remember because it was a while ago I was doing this video and I paused it. So let me go back and take a look at what I was doing, because I actually lost track of what I was doing, and I will be back in just a few moments. Okay, so it seems that we were talking about, we were over here and we got into, and we were doing actually this graph here. So I'm going to end this video here, and then in the next video we will continue with the graph, and then we will finish it in the next video. So I'll see you in the next video, and thank you.